All right, so we're jumping into a new chapter. This chapter is pretty abstract. It's all about chirality and isomerism. And so we're going to start off talking about chirality and what chirality means. Chirality is derived from a Greek word. So it's derived from the Greek word kyr, and what this means is hand. And so the way I like to describe chirality is the handedness of a molecule, right? So your left hand looks a lot like your right hand, but they are not the same, right? Yeah. If you lost your left hand and they got a hand transplant and transplanted a right hand on your old left hand position, you'd be mighty unhappy, right? You have very specific hands for very specific purposes. So I'll write oftentimes molecules have handedness. And so I'll show you an example of this. And this can be really abstract and three-dimensional. So if you have a model kit, this is where they come in handy. So let's just take a simple one. It's a tetrahedral carbon. And I'm going to draw a mirror plane down here. So the hydrogen is reflected, the fluorine is reflected, the bromine's reflected, and the chlorine is reflected. So if you look at these two molecules, they look really similar, right? They both have one bromine, one chlorine, one fluorine, and one hydrogen coming off a central carbon, but they're not the same molecule. If you take these two molecules and you try to overlay them atom for atom on top of one another, you can't do it, right? So for example, if you take the molecule on the left and you just spin it around like a top and try to overlay the chlorine, then the hydrogen will be where that fluorine is and the fluorine will be where the hydrogen is. There's no way of overlapping these molecules. Another way of thinking about this with a related analogy is if you take your right hand and left hand, you can't overlay them finger for finger, right? So these have their own unique handedness. So oftentimes when chemists are looking at chiral molecules, they say chiral molecules are non-superimposable on their mirror images. These must be chiral compounds or chiral molecules. All right. Does that make sense? It's kind of abstract. Yeah.
So basically, whatever your image about it, it's going to be a chiral molecule.
Yeah. So let's say you have some sort of compound and you're wondering whether or not it's chiral. The easy thing to do is to draw its theoretical mirror image and then ask yourself, is the mirror image the same? Can we overlap it atom for atom? Or can you not overlap it atom for atom? If you can't overlap the mirror image atom for atom, the original molecule must be chiral. We'll do a few practice problems and I'll show you what I mean by that. So let's do some practice. Let's determine if the following are chiral. And I'll give you an example. And in this example, I've got a cyclic ring system. What would this be named? 1,2-dimethyl cyclopentane. We got to be more specific though. We're missing something. Cis, right? So this would be cis 1,2-dimethyl cyclopentane. So kind of a mouthful. The question is whether or not this molecule is chiral. So what I'm going to do is I'm going to draw an imaginary mirror plane, right? And then we'll redraw the mirror image of this compound. Right, so that's a mirror image. I'm not the greatest at drawing pentagons, but you get the idea. Are these the same compounds? Can you overlay them atom for atom? Yeah, I think so. If you take this and you rotate it, I'm just going to spin this about its axis. See what I'm saying? Just kind of rotate it, spin it around. It's the exact same molecule, right? So what I would say is these are the exact same compounds, or this compound has a mirror image that is identical. Therefore, it is not chiral. Let me fix this C. Does that make sense? Let's try a different one, though. Let's do a harder one. This one will look very similar. So it's still 1,2-dimethylcyclopentane, but now it is trans, right? What I want you to do is to determine whether or not this compound is chiral and then check with your neighbors. So try drawing the theoretical mirror image or build it with your model kit and then build a mirror image model. So I'll give you a minute to think about whether or not this compound is chiral. This will make your head spin, huh? This is where model kits come in handy. If you're struggling with this, build the model and build the mirror image of that model side by side, and you can rotate them in space and see if you can overlay them perfectly on top of one another. Let's try this together. So I'll draw the mirror image. All right, if we look at this, they're not aligned in the same orientation, right? But what we can do is just like we did before, I'm going to rotate this and spin it around so that those methyl groups are now aligned. And if I do that, I've kind of spun it about 60 degrees. The methyl groups are now aligned with the original starting molecule. Can we overlay this atom for atom? No, not at all. So this compound has a non-superimposable mirror image. Therefore, it must be chiral. All right, let's do another one. All right, example number 3. This time I'm going to do an alkene. It looks like this. This is a cis alkene. Let's determine whether or not this is chiral. This one I think is a little bit easier because it's all planar. You don't have that three-dimensionality to it. So if we do this one and we think about its mirror image, we can say, well, its mirror image, I'll draw in blue. Is that the same? Of course it is. So it's identical. The mirror image is identical. Therefore, it is not chiral. I'll show you a really simple trick, though. Yeah?
So, like, when you're doing the example for one, you said rotate. So, is there atom that is going to be like center of the rotating?
So what I meant in the original practice problem was imagine this being an axis point, that red dot. I'm spinning it about that axis, just about 60 degrees. So I'm just taking it like this, spinning it over. That's all I'm doing is spinning around that red dot axis. Whenever you're rotating these, you can rotate them however you want. You can flip them over like pancakes. You can spin them around 360 degrees. It doesn't matter, right? So spatially, you can rotate them any direction you want in order to find a perfect overlap. Yeah?
Off of that last one, if we were to make the trans version of that, that would be non-chiral as well, correct?
Yeah, so the question for example 3 was, this was a cis alkene. What if we have a trans alkene? The trans alkene would be non-chiral as well. Yeah, so anytime you do these, draw the mirror image or build the mirror image with your model kit and see if you can rotate them and overlay them atom for atom on top of one another. Yeah.
So what if they're two cycles? And which one should be the
So if it's a bicyclic ring system, you can rotate it or spin it however you want. There's not really a center. You just got to find some way of rotating it or flipping it so you can overlay it atom for atom as best you can. Yeah. I'll show you a good trick though. And this trick works pretty well to identify non-chiral compounds, but won't help you always identify chiral compounds. If you have an internal plane of symmetry, you cannot be chiral. So let's go back up and see if we can apply this to some of our examples, and I'll show you what I mean by an internal plane of symmetry. So let's go and look at this one up here. You see how this compound has an internal mirror plane in it? So the left-hand side of the molecule is the exact same as the right-hand side. That means we know right off the back that it's not chiral. If we go up and do this one, though, and we try to draw a mirror plane, it's not the same on that left-hand side and right-hand side, right? So that one doesn't have an internal mirror plane. However, that being said, just because something doesn't have an internal mirror plane doesn't mean that it's automatically chiral. This only tells you if it's not chiral. And then we go up to compound 1. This one does have an internal mirror plane, so it's definitely not chiral. Yep.
So if it's not chiral, but then this doesn't always tell you if it's chiral, what's the thing that's in between? Is there something else that can be? Or?
Yeah, so the question was, if the internal mirror plane tells you if something's not chiral, what do you do to tell if it's chiral? You do exactly what we did here. Draw the mirror image and see if the original molecule can overlay on its mirror image. That's really the only way to ultimately check if a compound is chiral.
So then, not every not chiral molecule has that mirror.
So even I'm getting confused now. If you ever have an internal mirror plane, it means you're automatically not chiral. However, we'll see examples later where we might have to do conformational twists and things like that in order to find a mirror plane. Okay. So it might not off the back automatically look like it has an internal mirror plane. You might have to contort it or do a Newman projection rotation to find that mirror plane. Okay. Yeah.
Or is there an example of something that has an internal mirror plane but is chiral?
No. So the question was, is there an example of something that has a mirror plane but is chiral? No. Yeah. Good question. All right. So let's talk about one of the most common features that you'll find in chiral compounds, and these are called stereocenters. It's where you buy your car radio. That's a good chemistry joke. It's an atom that has 4 different substituents coming off of it. And they must be different. And one of those substituents can be a lone pair. And I'm going to put an asterisk here because there are always exceptions in chemistry, as you've probably learned. Nitrogen lone pairs don't count. Does anybody know why nitrogen lone pairs don't count? It's a bit weird. So think about ammonia, right? Ammonia is NH3. And you've got this lone pair sticking up like this. What happens really fast is that lone pair can actually tunnel through the nitrogen atom due to weird quantum mechanical behavior. And this can kind of flip inside out like an umbrella. Because of that, we can't really rely on the lone pair being in one spot. It's kind of flipping inside out really fast anytime you have a lone pair on a nitrogen. If you go down that column and you look at phosphorus, the lone pair can still do the same thing, but you have to apply a lot of heat to it. So you can't actually observe it at room temperature. You can't with nitrogen very easily. You'd have to cool it down really cold to get that lone pair to stay in one spot. All right, so nitrogen's kind of the oddball example. And I'll show you a simple trick too. Is I label these with a star. And I like red stars, so I'm just going to label it with red star. All right, and I'm going to make an important note. Often, but not always, welcome to chemistry, there's a million exceptions to everything. Chiral molecules have one or more stereocenter. There are exceptions to this, and we're going to cover those exceptions as we go through this chapter. So I'll show you some examples of chiral compounds, and we'll try to identify their stereocenters. Yep.
Question regarding the stereocenter. In your handout, you have a stereocenter with a carbon atom with a nitrogen, an NH2, a hydrogen, and a CH3 coming off of it, as well as another carbon. So it's the entire subgroup, not just the first molecule that's off of?
So the question was, what are you referring to as a substituent? Are you referring to the first direct attached atom or the entire thing coming off in 4 positions? We're looking at 4 entirely different groups. Don't focus on the first atom. The first atom doesn't necessarily tell you much. So let's say you have a central carbon, and one substituent's a hydrogen, another one's a methyl group, another one's an ethyl group, another one's an isopropyl group. That would be a stereocenter because each of those substituents is different from one another, right? Yeah, good question. So let's take a look at an example. And I want you to help me find the stereocenter in this. This is ibuprofen. Yeah, you can take I think up to like 1.5 grams of this stuff. I mean, this is a pretty rugged. It's how much?
1,300 milligrams.
So 3.2 grams per day you can have of this. It's a really good anti-inflammatory drug. So where's the stereo center in this? See if you can identify it and check with your neighbor. All right, who thinks they've identified the stereo center? All right, one common mistake people will make is they'll say, is this a stereo center right there? No, it has 2 identical methyl groups coming off of it. Can't be a stereo center. Then you can move up here and you can say, well, what about this one? It has 2 hydrogens. That can't be it. What about this one right here? It doesn't even have 4 things attached to it. It has 2 carbons and a hydrogen, so definitely not that. Can't be any sp2 hybridized carbons. What about this one? Yeah, absolutely. So what I mean by that is one version might have a methyl group as a wedge, and the other one might have it as a dash, right? So you could build this molecule 2 different ways. You could have that methyl group be a wedge or a dash, and if we look at the top one versus the bottom one, these are mirror images of one another, right? If you were to lay them side by side, they'd be mirror images that are no longer superimposable. So if we look at these are distinct different isomers of ibuprofen. So ibuprofen is sold as a 50-50 mixture of each of these. We'll talk about that in a little bit. 50-50 mix of each isomer. And what they refer to this as in the chemistry world is a racemic mixture. Oop. Racemic mixture. All right, you can, if you wanted to, give somebody only one isomer, so maybe you only give them the top one, that works. Or you can only give them the bottom one, that works too. They have marginally different efficiencies in your body as an anti-inflammatory drug, but not enough where it's worth the effort, time, or money to separate them out, so they just sell it as a 50-50 mixture. Yeah?
So you, previously on 1.1 you said that most of biological molecules are to one side of them. So it's just mainly cost that they would...
Yeah, so it's really, really expensive to make one isomer exclusively. It's really, really cheap to make a 50-50 mixture. We'll talk more about why that's the case later, but making a racemic mixture, piece of cake, no problem. Making one over the other, not so easy. Yeah?
Are there times where it would, like, not for ibuprofen, but for other compounds where it would prefer one of the chiral molecules over the other?
Yeah, let's take a look at an example of that. It's like I'm paying you. All right? Technically, you are paying me. What a deal. We'll talk about the labeling of these and the naming system of them next. All right, so this one looks pretty dang similar to ibuprofen. This is naproxen. So naproxen is another anti-inflammatory drug. Where's the chiral center in this one? Pretty much the same spot, right? So it's right there. So what we have, again, is we have 2 different versions of this molecule that are different handedness. So let me quickly draw this out. All right, so the methyl group on one could be a wedge versus this one down here, where that methyl group will be a dash. All right, this one is different though. This is not sold as a 50-50 mixture. So if we look at the one on the bottom, this one is an anti-inflammatory. I think it's 2 M's, right? I'm not the best with spelling, unfortunately. The top one will kill you. If you think about biology, right? Enzymes have very specific shapes, right? So often you're taught that lock and key paradigm. If you don't have the right size key, or maybe it's the mirror image for that matter, it won't fit in that lock. And in fact, it might fit in other locks that cause all sorts of bad problems, right? So in this case, this is not sold as a 50-50 mixture. Commercially, when they make this, they have to be very careful to make only the one shown on the bottom. Does that make sense? It's much more expensive, yeah. Historically, it's much more challenging to make one-handed molecules rather than a 50-50 mixture. Yeah?
So if it's more expensive and there is maybe not a very large risk, but a risk that one of those that will kill you atoms, let's say, is it a better anti-inflammatory or is it?
So the question was, is it better than ibuprofen? I believe so. And oftentimes you have multiple versions of anti-inflammatories in case you have somebody that maybe has a liver problem and can't take normal ibuprofen because you have to take it in a much higher dosage. So oftentimes there's different effective dosages of drugs too. Same thing with antibiotics too, right? So some antibiotics you might be allergic to, so you tell your doctor and they give you a different class of antibiotics. The same's true with anti-inflammatory drugs. Yeah.
So my question was more along the line of, if like you dumped things in a jar and it was going to make that, do you prefer to make one or the other, or is it just going to make it 50-50 if you don't do special things to try and make a specific one?
Yeah, so the question was, if you're trying to make this and you don't do anything special, you'll make a 50-50 mixture. The only way to make a chiral compound that's pure, meaning only one, like the top one or the bottom one, is through using another chiral compound to basically guide it into only making one over the other. It gets kind of complicated. Yeah.
So does that mean that there are natural chiral compounds?
Yeah, absolutely. So if you think about D-glucose, that's what we talk about a lot in biology. That is a natural chiral compound. So are our amino acids for the most part. Almost all of our amino acids are a specific handedness, and that has to do with the way nature provides them to us. Yeah. The ultimate question, if you want to get really philosophical, and I think I was talking about this in lab the other day, is if you can only make a chiral compound through the use of another chiral compound, where did the first chiral compound come from? I have no idea. Yeah.
This might be random, if you have like a 99-to-1 ratio of anti-inflammatory to will kill you, will you die, or is it?
Yes. So the question is, what ratio? Is this harmful? I'm not sure. Oftentimes your body can clear out a small amount of something that's toxic. The dose determines the poison for the most part. All right, so like I said, this is really important stuff, especially if you're thinking about going into pharmacy, medicine, anything like that. Knowing the handedness of a molecule and how to make only one-handed type of a molecule is of paramount importance. So what I've got for us next is to basically a system for distinguishing how to name the top one versus the bottom one. So if you got that handout, pull that out. All right, so in this handout, the first step says to identify any stereocenters in your molecule using a star. So like I said, stereocenters are the point where you have 4 different groups. If we look at this top position right here, I've got a nitrogen, so an NH2 group attached, a hydrogen attached, a CH3 group attached, and what would we call this group? A benzyl group, right? So we've got a benzyl group coming off. So definitely 4 different groups coming off of Adderall. Adderall, many of you have heard of, is used for what? ADHD, right? So this is another chiral compound. Next, what you want to do is to assign priorities to each substituent coming off of that stereocenter. And what I mean by that is you want to identify the heaviest attached atom that gets priority number 1. So in this case, nitrogen is heavier than carbon, right? So nitrogen gets priority 1 because it's the heaviest attached atom. And then between 2 and 3, we've got kind of a tie. They're both carbons, but hydrogen's definitely last, so we're going to number that one 4. The question is, well, why did I put 2 for the benzyl group and 3 for the methyl group? Well, in this case, it says if there's a tie, continue down that substituent till you find a difference. So for example, sorry, I'll come back to you. For carbon 2, we'd say, all right, if it's a carbon-carbon tie, what's coming off of carbon 2? Well, coming off of carbon 2, we have a carbon, that's right down here, right? And then we have 2 attached hydrogens, right? Versus carbon 3, what's attached to carbon 3 as we move further away from that stereocenter? 3 hydrogens. All right, tiebreaker says that this one must win, right? It has the next heaviest atom attached to it, therefore it's position 2, and then that methyl group's going to be position 3, right? All right, then number 3 says, have an arrow starting at position 1, go through position 2, and cross over into position 3. So in this case, it looks like we're doing a counterclockwise arrow. Does that make sense? And it says if your arrow is going clockwise or to the right, that means that it's an R configuration. Whoops, assuming that your lowest priority is pointing back. And if it's going counterclockwise, that it must be an S. So if we look at this one, our lowest priority is a dash, so we're following our normal rules. And we're going counterclockwise, so it must be an S stereocenter. Does that make sense?
Why is it an S?
Yeah, that's a good question. So it's easy to remember rotating to the right is R, right has R in it. The question is, well, why is left S? It actually goes back to the Latin root for left, which is sinister or sin rotatory. So in this case, why don't we shake hands with our left hand? Because it's untrustworthy, right? You want to shake with your right-handed person, or with your right hand. It used to be believed that left-handed things were inherently evil or less trustworthy. They used to teach kids to write with their left or with their right hand, even if they were right-handed, because of that. We don't do that anymore. Sorry, was there a question somewhere?
Yeah. So based upon which is the priority, you just based it off the first atom attached to the center, not the entire number.
Yeah, so the question was, when you're looking at your substituents, first thing you look at is the first atom immediately attached, right? So in this one, for example, nitrogen versus carbon versus carbon versus hydrogen, right? Nitrogen's the heaviest, so it got position 1. Then we had a carbon-carbon tie. That's why we had to go further out the chain, find the tiebreaker, and then give that number 2. The one after that was number 3, and then hydrogen being the lightest must have been number 4.
Completely straight to mass, and it's like, wait.
No, do not look at the complete group. You're only looking one atom out at a time. Yeah.
So, what if it's split? Like there's like a 1, a 2, a 3, and a 4.
I'm having trouble understanding.
So your arrow, it says go from 1 and then 2, 3, and then like if the 2 and the 3 are on opposite sides, how is that?
So basically, ignore substituent 4. Try to connect 1, 2, and 3 using a smooth arrow. If it's going to the right and your lowest priority is pointed backwards, it's automatically R.
If the hydrogen and the methyl group were switched.
Oh yeah, that would change. So the question was, what if the hydrogen was a wedge and the methyl group was a dash? Then we switch it from R to S. So let's go through and do an example one really quick. Let's do this one, and that might make more sense. So before we leave, let's just do one easier one. All right, so we know that this has a stereocenter, has 4 different groups coming off of it. All right, highest priority. What's the heaviest atom? Bromine. So that's priority 1. Next highest? Which one? Chlorine. All right, and then fluorine would be 3. Hydrogen's going to be 4, but we're kind of ignoring 4. It's just there, right? All right, so what we're going to do next is say, all right, we're going to connect 1, 2, and 3 with an arrow. So we're going counterclockwise. Counterclockwise is normally S. However, our lowest priority is coming towards us, so we want to switch from an S to an R configuration. So counterclockwise, but the lowest priority is forward. It must be an S configuration. Does that make sense? The normal rules apply if your lowest priority is a dash. If it's not a dash, just flip it to the opposite. Does that make sense? Because another thing you could do is instead of viewing it from this way where it's top down, flip it around and view it from bottom up, right? And then your lowest priority would be a dash and the rules would apply like normal. Oh, sorry. Holy cow. It should be an R. So we flipped from an S to an R. I was talking and writing at the same time and not following my brain. Yep.
So doing this, we always have to have our lowest priority facing away from us.
You can. If your lowest priority is pointing away from you, it's a lot easier. I'll say that. If it's not, just flip your assignment. It's as simple as that. So what we'll do tomorrow is we'll look at a lot harder examples with the tiebreaker rules and then learn what to do if we don't have a wedge or a dash for our lowest priority.